So the Euler's proof, and we're going to do it using the definition of one of the limits of the Euler's identity. So let's take e to the x, which is f of x equals e to the x, and let's apply the chain rule to it, or not the chain rule, the derivative from first principles, which is limit as h approaches e minus e over x over h. Essentially the change in output divided by change in input, which is what Isaac Newton figured out back in the day, and Leibniz as well. But using exponent identity, we can just rewrite this as that over h. So all we did was factor out an e to the x. Now, we can pull that e to the x out of the limit definition through the constant multiple rule. I don't know if they call it that with limits, but I do know they call it that with derivatives. So that means that's limit as h approaches 0 of e to the h minus 1 over h. Now, a lot of proofs you'll see will just tell you to assume that this is 1, unless you watch a few YouTube videos. So we're going to set that top one equal to some arbitrary value. And I would set it to x because that's typically what people want you to do. But I'm going to set it to n because when people define the Euler's identity, they define it a certain way. And I'll get to that a little bit later. So now let's solve for h because we can rewrite this as n divided by h. But we want h in terms of n. So what we're going to do is we're going to plus 1 to the other side equals h, or n plus 1. This is pretty confusing because h and n look pretty similar. We're going to log both sides. So we're going to get ln n plus 1. So that would be ln n plus 1 here. Now we're going to realize something. As h approaches 0, n approaches 0. Because as h is going closer to 0, we realize that we can, I guess, direct substitute in here to get e to the o minus 1 equals n, which is equal to 0. So as h approaches 0, so does n approach 0. So that means this entire top term is approaching 0. But we're going to do something interesting here, and we're going to multiply by the reciprocal of n on the top and bottom, which is essentially just multiplying by 1. And what we get is we get 1 over n ln 1 plus n. And 1 over n is essentially just going to be 1 over n. Second, I'm trying to. So we're going to use a kind of inductive kind of thinking here because we're going to go backwards from the logarithmic identity. Typically you'll bring the power down, but this time we're going to bring the exponent up. So it's going to be ln 1 plus n over 1 over n as the limit as n approaches 0. So that's simply going to be it's a little bit strange because typically what you'll see in the Euler's form is going to be 1 over ln 1 plus x over r divided by, or times, or to the power of r. But as we can see, the logic holds the same because they are both still approaching 0 as r is approaching infinity. Oh yeah, x divided by r in the top two, typically. So both hold the same logic. So that would mean that this entire term becomes 1 over the definition of Euler's identity, which is just that part, ln e. And what is ln e? It's just 1 over 1. So that just means that the derivative definition is ex times 1. Now, I remember proving the other one with something not with e to the x, so I'm going to try that again here. So let's assume that it's a to the x, and that would mean that it's a to the x plus h minus a over x over h. So again, same logic here. We're going to factor out the a over x over h. What I did was I rewrote a in terms of c variable so we can chain rule it out. So that means ah equals some form of e to the c equals to the e to the ch. So we're going to ln both sides to get h ln a equals ch, cross out the a, which means that ln a is equal to c. So that means h ln a is equal to a to the h. So we're going to put that into there to get a to the x ln a minus 1 over a certain variable h. But h can be rewritten as, I believe the way I did it was, yeah, so limit as h approaches. H ln a equals a to the h. So that would essentially be equal to a to the x ln a to the power of h, or e to the power of h a minus 1 divided by h. Oh yeah, I remember how I did it. So we realize that you can apply L'Hopital's rule here. So we can do a to the x times L'Hopital's rule, which is ln a times, let me just move all this, times the derivative of the inside, which is going to be ln a, simply because h is the variable that is changing, minus, not even minus 1, because the derivative of negative 1 is just 0, divided by 1. So guess what here? We can rewrite the top as ln a over h times ln a over 1, which is essentially just equal to a times ln a, ln a to the power of 1. But we notice that a to the h is approaching 0, so we can direct substitute it in, as L'Hopital's rule does state. So we get ln a. So this entire term is equal to ln a, such that we get the derivative of a ln a. So I figured this out myself, so I don't know if it actually holds. And I think it's quite circular because we use the derivative definition here, and then we use L'Hopital's rule. So we use the derivative of itself, essentially, by using chain rule and Euler's number, because we've already established in the first proof that the derivative of e to the x is equal to the e to the x. So we use a combination of that derivative and the chain rule to understand that form. So it works logically, but it would only work if you had extensive knowledge of calculus already. And I'm sure they figured out another proof for this, but fortunately for me, this one holds. So I wonder if anyone's done it like that. So